There are more stars in the observable universe than grains of sand on every beach and desert on Earth combined, and together they occupy less of space than a single proton occupies the Earth. That is not an approximation. That is not a rough estimate rounded for comfort. That is what the mathematics return when you actually sit down, calculate the volume of every star that exists, and compare it to the volume of the universe that contains them. The answer has 48 zeros after the decimal point. Before you reach the first meaningful digit, you have spent your entire life looking at the night sky. All that light scattered across the darkness, all that glittering suggestion of abundance and density and cosmic richness is a trick played by distance. Your eyes are collecting photons from the nearest sliver of your own galaxy and reporting back that the universe is full. It is not. The real universe, the one that stretches beyond what your eyes can reach and beyond what most telescopes can penetrate, is a darkness so deep and so permanent that the word empty is almost too small to describe it. And tonight, we are going to walk into that darkness together. We are going to follow the science all the way to its most unsettling conclusions, and we are not going to look away from what we find. If this is the kind of journey you want to take more often, subscribing to the channel takes just a moment, and it means we can keep making nights like this one possible for everyone who needs them. By the time we are finished, the universe will look nothing like it did when you sat down. Let us begin. Look up on a clear night, far from city lights, and the sky looks full, stars everywhere, thousands of them scattered across the blackness like someone threw a handful of salt across a dark table. The Milky Way stretches overhead like a glowing river. Nebulae glow faintly if you know where to look. It feels rich. It feels crowded. It feels like the universe is packed with stuff. That feeling is wrong. Every star you can see with your eyes belongs to your immediate neighborhood. The farthest ones sit maybe 15,000 light years away. That sounds enormous, and by any human standard it is. But the Milky Way stretches 100,000 light years across. You are seeing less than 15% of your own galaxy, and your galaxy is one of hundreds of billions. Think about what that means. You are standing in your backyard, looking at the trees and the houses on your street, and concluding that the entire planet must be covered in suburbs. You have not seen the oceans. You have not seen the deserts. You have not seen the vast stretches of ice at the poles where nothing lives and nothing moves. You are drawing a picture of the whole world based on your view from the porch. Now here is where things get uncomfortable. Let us add a telescope and see what the universe actually looks like when you stare past those nearby stars. In 1995, astronomers pointed the Hubble Space Telescope at a tiny patch of sky in the constellation Ursa Major. This patch was small, absurdly small. If you held a grain of sand at arm's length against the sky, that grain would cover it. There was nothing visible there. No stars, no light, no hint of anything. Just blackness. They left the telescope staring at that emptiness for 10 straight days. Long exposure after long exposure, collecting every photon that drifted in from the dark. When the image came back, it contained roughly 3,000 galaxies. Not stars. Galaxies. Each one holding hundreds of billions of stars. 3,000 entire galaxies hiding behind a grain of sand. And when they repeated the experiment in other patches of sky, other directions, other seemingly empty regions, the result was the same. Galaxies everywhere. In every direction. At every distance. The darkness was not empty. It was full of light too faint and too far away for your eyes to catch, so surely the universe must be full. Right? Trillions of galaxies, each with billions of stars, scattered in every direction. How could that possibly be empty? Here is where we need to stop feeling and start counting. The observable universe is roughly 93 billion light-years across. It contains approximately 2 trillion galaxies. Each galaxy holds, on average, about 100 billion stars. That gives us roughly 200 billion trillion stars. Written out, that is a 2 followed by 23 zeros. It sounds like more than enough to fill anything. But now ask a different question. How much space do those stars actually take up? A typical star like the Sun is about 864,000 miles across. You can calculate its volume using simple geometry. Do that for every star in the observable universe. Add them all up. Every single one. The total volume of all the stars in existence comes to roughly 2.8 times 10 to the 32nd power cubic miles. That number looks huge until you set it against the volume of the observable universe itself, which is approximately 3.6 times 10 to the 80th power cubic miles. Divide the first number by the second, and you get the fraction of space that stars occupy. It comes out to about 7.8 times 10 to the negative 49th power. That is a decimal point followed by 48 zeros and then a 7. Let me make that physical for you. If you shrank the entire observable universe down to the size of Earth, all the stars that exist, every single one of those 200 billion trillion burning furnaces of hydrogen and helium would occupy a volume smaller than a single proton. Not an atom. A proton. The tiny dense speck at the center of an atom. And even that comparison is generous, because stars themselves are mostly empty space. An atom is almost entirely nothing. The nucleus at its heart takes up about 1 trillionth of the atom's volume. The rest is a cloud of probability where electrons might or might not be. So the matter inside stars is itself mostly vacuum. Emptiness inside emptiness inside emptiness. But we have only talked about the stuff inside galaxies. The space between stars is staggering all by itself. The nearest star to our Sun, Proxima Centauri, sits about 4.25 light-years away. That is roughly 25 trillion miles of nothing between 2 points of light. If you shrank the Sun to the size of a grain of sand, 1 millimeter across, Proxima Centauri would be another grain of sand sitting about 19 miles away. 19 miles of empty table between 2 specks of dust. That is the spacing inside our galaxy, one of the denser places in the universe. Between galaxies, the emptiness becomes almost impossible to describe. Our nearest large neighbor, the Andromeda Galaxy, is 2.5 million light-years away. The Milky Way is 100,000 light-years wide, so the distance to Andromeda is 25 times the width of our entire galaxy. Using our grain of sand scale, it is like placing 2 grains a football field apart and calling everything between them your neighborhood. And between those 2 galaxies, there is almost nothing. A handful of tiny dwarf galaxies. Some wisps of gas so thin they make a laboratory vacuum look crowded. Mostly just darkness, silence, and the slow expansion of space itself. This is the reality the night sky hides from you. The light your eyes collect comes from a tiny nearby bubble. Step outside that bubble, and the universe is a void so vast and so total that the word emptiness barely scratches its surface. But here is what no one tells you. We have not even found the deepest layer of this problem yet. Because even if you add up all the stars, all the gas, all the dust, all the planets, all the moons, every scrap of matter you could ever see or touch or measure with any instrument ever built, you are still missing most of what the universe contains. And what you are missing is something far stranger than empty space. So the space between stars is enormous. But stars at least have neighbors. They live in galaxies, and inside a galaxy you are never truly alone. The Sun has Proxima Centauri 4 light-years away. Other stars sit at similar distances in every direction. The Milky Way holds 200 billion of them, scattered across a disk 100,000 light-years wide. Dense by cosmic standards, but galaxies themselves are lonely things. Step outside the Milky Way, and you enter a kind of emptiness that has no comparison in everyday life. Our nearest large neighbor, Andromeda, sits 2.5 million light-years away. Between us and Andromeda, there is almost nothing. A few small dwarf galaxies, some scattered hydrogen atoms drifting in the void. And silence. That gap is 25 times wider than our entire galaxy, and this is considered a crowded neighborhood. The Milky Way and Andromeda belong to something called the Local Group, a collection of about 80 galaxies held together by gravity. Most of them are tiny dwarfs you would never notice without a powerful telescope. The whole group stretches roughly 10 million light-years across. Beyond it, the emptiness deepens. The nearest large galaxy cluster is the Virgo cluster, about 54 million light-years away. It contains around 2,000 galaxies. Between us and Virgo, there are scattered galaxies here and there, but mostly open space. If you could fly from the Milky Way toward Virgo at the speed of light, you would travel for 54 million years. And for almost the entire journey you would see nothing close enough to touch, just distant points of light, slowly shifting, with unimaginable gulfs between them. Now zoom out further. Galaxy clusters themselves group into even larger structures called superclusters. Our local group is part of the Laniakea supercluster, which contains roughly 100,000 galaxies, spread across 500 million light-years. It sounds massive and crowded, but do the math on the density, and the picture changes completely. Spread 100,000 galaxies across a volume 500 million light-years wide, and each galaxy occupies, on average, a bubble of space about 5 million light-years across all to itself. That is 50 times the width of the Milky Way. For a single galaxy to rattle around in, like placing a marble inside a cathedral, and saying the cathedral is full. And between superclusters, the emptiness reaches its most extreme form. There are regions of space hundreds of millions of light-years across that contain almost no galaxies at all. We will get to those later. For now, the point is this. At every scale you examine, the universe is mostly nothing between atoms, between stars, between galaxies, between clusters, between superclusters. Each level of zoom reveals more void than the last, but here is the number that puts all of it into perspective. The average density of the entire observable universe is approximately 6 hydrogen atoms per cubic meter. 6 atoms. In a space the size of a small box you could hold in your hands, everything else in that box is vacuum, darkness, nothing. And those 6 atoms are not spread evenly. Most of them are clustered in galaxies, which means the space between galaxies is even emptier than the average suggests. In the vast stretches between galaxy clusters, density drops to less than 1 atom per cubic meter. Some regions contain less than 1 atom per 10 cubic meters. You could fly through that space for billions of miles and never hit a single particle. For comparison, the best vacuum we can create on Earth inside the most advanced laboratory chambers still contains about 10 billion molecules per cubic meter. The space between galaxies is billions of times emptier than the emptiest vacuum we can produce. Our best attempt at nothingness is thick fog compared to what the universe does effortlessly across most of its volume. Now here is where something strange happens. Take all of this visible matter, every star, every planet, every cloud of gas and dust, every atom of hydrogen drifting alone between galaxies, add it up. Everything you could ever see, touch, or detect with any instrument that measures light or heat or radio waves. It accounts for about 5% of the universe. 5%. That number deserves a moment of silence. We spent the last several minutes marveling at how little visible matter there is, how thin it is spread, how absurdly empty space is, even when you count every atom in existence. And now you learn that everything we counted, all of it, is a tiny leftover. A rounding error. The universe is 95% something else. 27% is a substance called dark matter. We cannot see it. We cannot touch it. It does not glow or reflect light. It does not interact with any telescope ever built. But it has mass, and that mass pulls on everything around it with gravity. We know it is there because without it, the math does not work. Galaxies spin too fast. Clusters hold together too tightly. The universe has more gravitational pull than visible matter can explain. Something massive is hiding in plain sight, and we have no idea what it is. The remaining 68% is even stranger. It is called dark energy, and it is not a substance in any way you would recognize. It is a property of space itself, a pressure that pushes the universe apart, accelerating the expansion of everything. We do not know what causes it. We do not have a working theory that explains its strength. We only know it is there. Because the universe is flying apart faster every second. And nothing in visible matter or dark matter can account for that acceleration. So step back and look at the full picture. You live in a universe where 95% of everything is invisible, unexplained, and fundamentally unknown. The 5% you can see is spread so thin across such staggering distances that it occupies less of the universe than a proton occupies the Earth. And even inside that 5%, most of what exists is hydrogen gas drifting between galaxies, never forming stars, never becoming anything interesting. The matter that makes up planets and people. And everything you have ever experienced is a fraction of a fraction. This should feel like the ground shifting beneath you. We like to think of ourselves as part of a universe rich with matter and light. We look at the night sky and see abundance, but the truth is, we are a vanishingly thin film of complexity, stretched across a void so deep it has no bottom, and most of that void is made of things we cannot name. The question then is how we know the invisible part is real. How do you detect something you cannot see, cannot touch, and cannot measure with light? The answer begins with a Swiss astronomer in the 1930s, who noticed that the galaxies around him were moving in ways that made no sense, and when he announced what he had found, nobody believed him. In 1933, a Swiss astronomer named Fritz Zwicky was studying a group of galaxies called the Coma Cluster. This cluster sits about 320 million light-years away and contains over 1,000 galaxies, all orbiting a common center of gravity like bees circling a hive. Zwicky wanted to measure the cluster's mass. He had two ways to do it. The first method was straightforward. Look at all the galaxies, measure their brightness, estimate how many stars each one contains, and add up the total mass. Light tells you how much matter is shining. More light means more stars means more mass. Simple. The second method was more clever. Measure how fast the galaxies are moving. If the cluster is held together by gravity, then the speed of its galaxies tells you how much total mass is pulling on them. Faster galaxies mean stronger gravity. Stronger gravity means more mass. This is the same logic you use when you watch water swirl down a drain. The speed of the swirl tells you something about the force pulling it. Zwicky did both calculations, and they did not agree. The galaxies were moving far too fast, based on the light he could see. The cluster did not have nearly enough mass to hold itself together. The galaxies should have been flying apart in every direction, scattered like sparks from a fire. But they were not flying apart. They were orbiting, bound together, behaving as though something enormous and invisible was gripping them. Zwicky ran the numbers again. The cluster needed roughly 400 times more mass than he could see. 400 times. Not a small correction, not a minor adjustment. The visible matter was a tiny fraction of what gravity demanded. He proposed that most of the mass must be invisible. Dark. Matter that has weight and pulls with gravity, but does not shine, does not glow, does not interact with light at all. He called it dark matter. Nobody took him seriously. The idea sounded ridiculous. Invisible matter that outweighs everything you can see by hundreds to one? Scientists assumed Zwicky had made a mistake. Maybe his measurements were off. Maybe the cluster was not really held together. Maybe he was wrong about how gravity works at those distances. So the idea sat on a shelf for 4 decades, gathering dust while the universe kept its secret. Then Vera Rubin came along. In the 1970s, Rubin was studying spiral galaxies. She wanted to measure how fast stars orbit the center of their galaxy at different distances. In our own solar system, this is easy to predict. Mercury, the closest planet to the Sun, orbits the fastest. Neptune, the farthest, orbits the slowest. Gravity weakens with distance. The farther you are from the central mass, the slower you move. This is basic physics, understood since Newton. Galaxies should follow the same rule. Stars near the center, where most of the visible mass is concentrated, should orbit quickly. Stars in the outer edges should orbit slowly. Because they are far from the bulk of the matter, the orbital speed should drop off smoothly as you move outward, like the speed of planets drops off as you move from Mercury to Neptune. That is not what Rubin found. She measured galaxy after galaxy, carefully plotting the speeds of stars at different distances from the center. And in every galaxy she studied, the outer stars were moving just as fast as the inner ones, sometimes faster. The speed did not drop off. It stayed flat or even rose slightly at the edges. This was impossible, unless there was more mass out there, mass that did not shine, mass that extended far beyond the visible edge of the galaxy, providing extra gravitational pull that kept those outer stars moving at high speed. Rubin had independently confirmed what Zwicky had proposed 40 years earlier. Galaxies contain far more mass than you can see. The visible stars and gas account for only about 15% of a galaxy's total mass. The other 85% is invisible. And it was not just one galaxy, it was every galaxy she measured. Every single one showed the same pattern. Flat rotation curves extending far beyond where the light ends. Something massive and invisible wrapping around every galaxy like a shell. The scientific community could not ignore this. One strange result from Zwicky could be dismissed. Dozens of identical results from Rubin could not. Dark matter became real. Since then, the evidence has piled up from every direction. Galaxy clusters bend light from objects behind them, a phenomenon called gravitational lensing. The amount of bending tells you how much mass is doing the bending, and it is always far more than the visible matter can account for. The cosmic microwave background, the faint afterglow of the Big Bang, shows temperature patterns that only make sense if dark matter existed in the early universe, shaping how matter clumped together. Computer simulations of the universe's evolution produce realistic galaxies and cosmic structures only when dark matter is included. Remove it and the simulations produce nothing that looks like the real universe. Every independent line of evidence points to the same conclusion. For every kilogram of normal matter in the universe, protons, neutrons, electrons, the stuff that makes up atoms and stars and you, there are approximately 6 kilograms of dark matter. It outweighs everything you have ever seen or touched by 6 to 1, and here is the part that should keep you awake at night. We do not know what it is. We have been searching for decades. Scientists have built detectors deep underground, shielded from cosmic rays, waiting for a dark matter particle to bump into a normal atom. They have smashed particles together at the Large Hadron Collider, hoping to create dark matter in the wreckage. They have aimed telescopes at regions of space where dark matter should be dense, looking for faint signals from dark matter particles interacting with each other. Nothing confirmed. Hints, maybe, possible signals that could be noise. But no definitive detection. The leading candidate is something called a WIMP, a weakly interacting massive particle, heavier than a proton but interacting with normal matter so rarely that catching one is like trying to catch a specific raindrop in a hurricane. Other candidates include axions, particles so light that trillions of them could pass through your fingertip, without a single one touching anything. There are even proposals that dark matter might be primordial black holes, formed in the first moments after the Big Bang. We do not know. We genuinely do not know, and it is passing through you right now. Billions of dark matter particles flowing through your body every second, through the walls of your room, through the floor, through the planet itself. It does not collide with your atoms. It does not push against your skin. It slides through you like you are made of smoke. The only trace it leaves is gravity, a pull so faint on human scales that you could never feel it. But on the scale of galaxies, that pull is everything. It is the reason galaxies hold together, the reason stars orbit instead of scattering, the reason you exist at all. This is the strange truth hiding behind every telescope image of a beautiful spiral galaxy. What you see, the bright arms of stars, the glowing clouds of gas, the dark lanes of dust, that is the small part. The garnish. The visible galaxy sits inside a halo of dark matter, 6 times more massive and several times larger, extending far beyond the edge of the last visible star. When you look at a photograph of the Milky Way, you are seeing less than 10% of what is actually there, and if dark matter is unsettling because it is invisible and unknown, what comes next is worse. Because dark matter at least behaves like matter. It has mass, it clumps, it pulls things together. The next piece of the puzzle does the opposite. It pushes. And it is winning. Here is a question that sounds simple, but leads somewhere unsettling. If dark matter is invisible and barely interacts with anything, what does it actually do? Why does it matter that the universe is full of something we cannot see or touch? The answer is that without dark matter, you would not be here. No galaxies, no stars, no planets, no life, nothing but a thin, cooling fog of hydrogen and helium spreading forever into darkness. To understand why, you need to go back to the beginning. Not the very beginning, not the first fraction of a second, but to a time about 380,000 years after the Big Bang. By that point, the universe had cooled enough for the first atoms to form. Hydrogen and helium, the 2 simplest elements, filled all of space in a nearly uniform cloud. Nearly uniform, but not perfectly uniform. There were tiny differences in density. Some regions were 1 part in 100,000 denser than average. Others were 1 part in 100,000 thinner. Those tiny differences are the seeds of everything you see today. Every galaxy, every star, every planet grew from a region that started out slightly denser than its neighbors. Gravity did the rest. A denser region pulls on surrounding gas. More gas falls in, making the region denser still. That pulls in more gas. Over hundreds of millions of years, these seeds collapsed into the first structures. But here is the problem. Normal matter does not collapse easily. When a cloud of hydrogen gas compresses under gravity, it heats up. Hot gas emits radiation, light, and heat streaming outward. That radiation pushes back against the collapse. It creates pressure that fights gravity. The gas wants to fall inward, but radiation pressure pushes it outward. These two forces battle each other, and in the early universe, they were nearly balanced. Think of it like trying to squeeze a balloon. You push inward, but the air inside pushes back. You can compress it a little, but the harder you squeeze, the harder it resists. Normal matter in the early universe worked the same way. Gravity squeezed, radiation pushed back, and the tiny density differences, 1 part in 100,000, were not strong enough for gravity to win on its own. This is where dark matter changes everything. Dark matter does not interact with light. It does not emit radiation. It does not absorb radiation. It does not feel radiation pressure at all. When gravity pulls dark matter inward, there is nothing pushing back. No balloon effect. No resistance. Dark matter simply falls, freely and silently, into whatever gravitational dip it encounters. So in the early universe. While normal matter was stuck in its tug of war between gravity and radiation, dark matter was already collapsing. It gathered into clumps, forming structures called halos. These halos were enormous, roughly spherical clouds of dark matter held together by their own gravity. They formed long before any galaxy existed, long before any star ignited, and they created something crucial: gravitational wells, deep pits in the fabric of space-time, where gravity was significantly stronger than in the surrounding space. Imagine digging holes across a flat landscape and then pouring water over the surface. The water flows into the holes and collects there. The holes do not care what the water is doing on the surface. They just pull it in. Dark matter halos were those holes. Normal matter, the hydrogen and helium gas, was the water. Once the dark matter had carved out gravitational wells, normal matter fell into them. The gas concentrated. Density increased. And now, inside these wells, the gas was dense enough for gravity to finally overcome radiation pressure. Collapse began in earnest. The first clouds of gas fragmented into smaller clumps. Those clumps compressed further. Temperatures at their cores climbed to millions of degrees, and then, roughly 100 million years after the Big Bang, the first stars ignited. Those first stars were monsters, hundreds of times the mass of our Sun. They burned through their hydrogen fuel in just a few million years, then exploded as supernovae, scattering heavier elements, carbon, oxygen, iron, into the surrounding gas. Later generations of stars formed from this enriched material. Smaller, longer-lived stars like our Sun. Planets formed from the leftover debris. Chemistry became possible. And eventually, on at least one small rocky world orbiting an ordinary star, life began. Every step in that chain traces back to dark matter halos forming first, and pulling normal matter into the wells they created. Without that invisible scaffolding, the seeds of structure would have been too weak. The gas would have stayed spread out, gently expanding with the universe, never dense enough to ignite a single star. This is not speculation. Computer simulations confirm it with striking precision. Astrophysicists run models of the early universe with and without dark matter, include dark matter, and the simulation produces a cosmos that looks remarkably like ours. Galaxies form at the right times. They cluster into groups and filaments in patterns that match observations. Stars appear, evolve, and die in ways that produce the chemical elements we find in real nebulae and real planets. Remove dark matter from the simulation and everything falls apart. Gas never concentrates enough. Galaxies never form. The universe stays a featureless soup of hydrogen and helium, slowly cooling, slowly thinning, forever. So when you look at the Milky Way stretched across the sky, you are looking at a visible structure sitting inside an invisible one. The galaxy's bright disk of stars is roughly 100,000 light-years across. Its dark matter halo extends at least 600,000 light-years in every direction, 6 times wider than the visible galaxy, and the halo contains about 10 times more mass than all the stars and gas you can see combined. Picture an iceberg. The part above the water is beautiful, sculpted, gleaming in sunlight. But 90% of the iceberg is below the surface, invisible, massive, and absolutely essential to everything the visible part does. The visible galaxy is the tip of the iceberg. The dark matter halo is the mountain of ice beneath the waves. And every galaxy has this structure, not just the Milky Way. Every spiral galaxy, every elliptical galaxy, every dwarf galaxy huddled in the outskirts of a cluster. Each one sits at the center of a dark matter halo that dwarfs it in size and mass. The bright, beautiful galaxies we photograph with our telescopes are decorations on a hidden framework, ornaments on an invisible tree. This framework is what makes the universe's emptiness so strange. The visible universe is almost entirely void. But the invisible universe, the dark matter scaffolding, is spread even more widely, filling halos that extend far beyond every galaxy's visible edge. There is more invisible structure than visible structure, more hidden architecture than anything our eyes or instruments can directly detect. And yet, even with dark matter and normal matter combined, we have only accounted for 32% of what the universe contains. The remaining 68% is something else entirely. Something that does not build structure, something that does not pull matter together, something that does the opposite, pushing the universe apart at an accelerating pace. And when 2 teams of astronomers stumbled onto this force in 1998, it did not just surprise them, it frightened them. In the 1990s, 2 teams of astronomers set out to answer what seemed like a straightforward question. The universe is expanding. Everyone knew that since Edwin Hubble proved it in 1929. But gravity should be slowing that expansion down. Every galaxy pulls on every other galaxy. All that mass, all that gravitational attraction should act like a brake. The real question was how strong the brake was. Would the universe slow down and eventually stop? Would it reverse and collapse back on itself in a big crunch? Or would it keep expanding forever, just more and more slowly? To find out, you need to measure how fast the universe was expanding at different times in the past. And to do that, you need a cosmic ruler, something whose true brightness you know, so that when you observe it from Earth, you can calculate exactly how far away it is based on how dim it appears. The perfect ruler turned out to be a specific type of exploding star called a Type 1 supernova. Here is why these explosions are so useful. A Type 1 supernova happens in a 2-star system. One star is a white dwarf, the dense leftover core of a dead star, roughly the mass of the Sun crushed down to the size of Earth. The other is a normal living star. The white dwarf pulls matter from its companion, stealing gas from its surface. That stolen material piles up on the white dwarf, adding to its mass gram by gram, year by year. When the white dwarf reaches exactly 1.4 times the mass of the Sun, a threshold called the Chandrasekhar limit. Something catastrophic happens. The pressure at its core crosses a breaking point. Carbon fusion ignites in a runaway chain reaction. The entire star explodes in seconds. Not partially. Completely. It releases as much energy in that moment as the Sun will produce over its entire 10 billion year lifetime. The critical detail is that this always happens at the same mass. Every Type 1 supernova detonates at 1.4 solar masses, which means every one releases roughly the same amount of energy, which means every one reaches roughly the same peak brightness. They are identical explosions happening across the universe at different distances. This makes them perfect measuring sticks if you know how bright something truly is, and you measure how bright it appears from where you stand. The difference tells you exactly how far away it is. Twice as far means 4 times dimmer. 3 times farther means 9 times dimmer. Simple inverse square law. 2 independent teams took on the project: the High Z Supernova Search Team and the Supernova Cosmology Project. Different scientists, different telescopes, different methods. They would cross-check each other. They spent years hunting for distant Type 1 supernovae, billions of light years away, measuring their distances, measuring their redshifts, the stretching of their light caused by the expansion of space, which tells you how fast a galaxy is moving away from you. By comparing distance to redshift for supernovae at many different distances, they could map how the expansion rate had changed over billions of years. Everyone expected to find the expansion slowing down. The only question was how much. In 1998, both teams announced their results, independently, using separate data and separate analysis. The distant supernovae were dimmer than expected, not by a huge amount, but by a statistically significant amount. Dimmer means farther away. Farther away than predicted means the universe had expanded more than the models allowed, and the only way to make that work is if the expansion was not slowing down at all. It was speeding up. The universe is accelerating apart, not coasting, not braking, accelerating. Something is pushing space itself to stretch faster and faster with every passing moment, and that something is overpowering all the gravity of all the matter and all the dark matter in the entire universe. Many physicists refused to believe it at first. Accelerating expansion violated every expectation. Gravity pulls things together. Nothing in the known physics toolkit pushes space apart. There had to be an error, bad data, miscalibrated instruments, something. But both teams found the same result independently. And over the following years, as more supernovae were observed at greater distances with better telescopes, the signal only grew stronger. Other lines of evidence confirmed it. The patterns in the cosmic microwave background, the distribution of galaxy clusters across space, the geometry of the universe itself, everything pointed to the same conclusion. The acceleration is real. Scientists gave the unknown cause a name: dark energy. But the name is a label for ignorance, not understanding. We do not know what dark energy is. We do not know why it exists. We do not know if it will stay constant or change over time. We only know what it does. It pushes, and it is winning. Here is the part that should make you sit up. Dark energy makes up approximately 68% of everything in the universe. Not a small contribution, not a secondary effect. It is the dominant component of reality. Dark matter accounts for 27%. Normal matter, everything you have ever seen or touched or tasted, every star and planet and grain of sand and molecule in your body, accounts for 5%. You live in a universe where 95% of everything is stuff humanity does not understand. We can measure dark matter's gravitational effects, but cannot identify it. We can measure dark energy's influence on expansion, but have no accepted theory for what generates it. The 5% we do understand is scattered so thinly, across such incomprehensible distances, that it might as well not exist in most locations. And here is the truly disturbing implication. Dark energy is not just pushing the universe apart, it is pushing it apart faster every day. The acceleration compounds. More expansion creates more space. More space means more dark energy, because dark energy appears to be a property of space itself. More dark energy means faster expansion, which creates more space, which creates more dark energy. It is a feedback loop with no off switch, and it means the universe is not just empty now, it is becoming emptier. The distances between galaxies are growing, the voids between cosmic structures are widening, and the rate at which all of this happens is increasing. If dark matter is the invisible scaffolding that built everything, dark energy is the invisible force tearing that scaffolding apart. One created the conditions for galaxies and stars and life. The other is methodically dismantling those conditions, stretching them thinner and thinner, pushing every island of light farther from every other island, until eventually the darkness between them becomes permanent and uncrossable. But before we trace where that process leads, there is a deeper mystery hiding inside dark energy itself. Because when physicists tried to calculate how much energy empty space should contain, they got an answer so spectacularly wrong that it might be the single worst prediction in the entire history of science. The simplest explanation for dark energy is that it belongs to space itself, not to any object or particle or field sitting inside space, but to the fabric of the vacuum. Empty space, according to this idea, has energy, a tiny amount per cubic meter, but an amount that adds up across the staggering volume of the universe to become the dominant force shaping reality. This sounds strange. How can nothing have energy? But quantum mechanics has been telling us for almost a century that empty space is not truly empty. It is alive with activity. In quantum field theory, every point in space is filled with fields: electromagnetic fields, electron fields, quark fields, and many others. These fields never sit perfectly still. They vibrate and fluctuate constantly, even in their lowest energy state. Think of the surface of a calm lake, even when no wind blows and no boats pass. The surface is never perfectly flat. There are tiny ripples, microscopic disturbances caused by the random motion of water molecules. Quantum fields behave the same way, even in their ground state. Their quietest possible configuration, they shimmer with residual energy. These fluctuations produce something remarkable. Particle-antiparticle pairs pop into existence from nothing, borrow energy from the vacuum for an impossibly brief moment, then annihilate each other and vanish. They appear and disappear so quickly that you cannot observe them directly, but their effects are measurable. They shift the energy levels of atoms by tiny amounts. They create a small attractive force between metal plates placed very close together, a phenomenon called the Casimir effect, which has been confirmed in laboratories. So the vacuum is not empty, it buzzes with quantum activity. And all that activity contributes a baseline energy density to every cubic meter of space. This baseline energy is called vacuum energy, and it is the most natural candidate for dark energy. If every cubic meter of space contains a fixed amount of energy, then as the universe expands and creates more space, the total vacuum energy increases. More energy means more repulsive pressure. More pressure means faster expansion. This matches what we observe. Einstein actually anticipated something like this. In 1917, he added a term to his equations of general relativity, called the cosmological constant. He did it for the wrong reason. At the time, everyone believed the universe was static, eternal, and unchanging. But Einstein's equations said the universe had to be either expanding or contracting. Gravity would not allow it to stay still, so he added a repulsive term to balance gravity and keep everything frozen in place. When Edwin Hubble discovered that the universe actually is expanding, Einstein dropped the cosmological constant and reportedly called it his biggest blunder. But 80 years later, the 1998 supernova observations suggested he may have been right after all, just for different reasons. The cosmological constant might be real, not as a fix to keep the universe static, but as the energy of empty space driving accelerating expansion. So far, so elegant. The vacuum has energy. That energy causes expansion to accelerate. The math works. The observations match. But here is the problem. The worst problem in all of physics. When theoretical physicists calculate how much vacuum energy, quantum field theory predicts they get a number, and when observational astronomers measure how much vacuum energy the universe actually has, they get a different number. These two numbers do not merely disagree, they disagree by a factor of 10 to the 120th power. Let me write that out so you can feel it. The theoretical prediction is wrong by a factor of 1, followed by 120 zeros. That is not being off by 10%, or even by a million. It is being wrong by more orders of magnitude than there are atoms in the observable universe. This is called the cosmological constant problem, and it is arguably the biggest unsolved puzzle in all of theoretical physics. Something in our understanding is catastrophically broken. Either quantum field theory is making a fundamental error in how it calculates vacuum energy, or there is some unknown mechanism that cancels out almost all of the predicted energy, leaving only the tiny residual amount we observe. But that cancellation would have to be impossibly precise. Imagine you owe someone a debt of exactly $100 trillion, and they owe you a debt of $100 trillion minus 1 penny. The two debts nearly cancel, leaving 1 penny. What mechanism could produce such an exact but imperfect cancellation? Nobody knows, and nobody has a convincing proposal. Some physicists think the answer lies in a theory we have not discovered yet, some deeper principle that naturally sets the vacuum energy to its observed value. Others suggest the answer involves the multiverse. Perhaps there are countless universes, each with different values of vacuum energy. Most of them are uninhabitable. Universes with too much vacuum energy expand so fast that no galaxies ever form. Universes with negative vacuum energy collapse. We find ourselves in a universe with just the right amount, simply because we could not exist in any other kind. This is the anthropic argument, and it bothers many physicists because it does not feel like an explanation. It feels like giving up. There are alternative models for dark energy that avoid some of these problems. One is called quintessence, named after the ancient concept of a fifth element beyond Earth: water, air, and fire. In quintessence models, dark energy is not a fixed property of the vacuum. It is a dynamic field that can change over time. Its energy density might have been different in the past, and might be different in the future. This opens unsettling possibilities. If dark energy grows stronger over time, the acceleration of expansion will increase. Structures that are safe today, gravitationally bound galaxies, solar systems, even atoms, could eventually be torn apart. If dark energy weakens, the acceleration might slow or even reverse, potentially leading to a big crunch where everything collapses. Current observations suggest dark energy has been roughly constant for billions of years. There is no evidence it is changing, but our measurements only span a small window of cosmic time, and the precision needed to detect slow changes is at the edge of what our instruments can achieve. So, we are left with this. The dominant component of the universe, 68% of everything, is a force we cannot explain, generated by a mechanism we do not understand, predicted by our best theory to be 120 orders of magnitude, stronger than it actually is, and it is actively reshaping the cosmos, stretching space, diluting matter, and driving every unbound structure in the universe farther from every other. But dark energy does not act in a featureless void. It acts on a universe that has shape. Structure. Architecture. And when astronomers finally mapped that architecture in 3 dimensions, they found something no one predicted. The universe is organized into the largest pattern ever discovered, a web of light surrounding cathedrals of absolute nothing. For most of human history, we assumed galaxies were scattered more or less randomly through space, some closer together, some farther apart, but no real pattern, like raindrops on a window. But in the 1970s and 80s, astronomers began measuring not just where galaxies appear on the sky, but how far away they are. They used redshift, the stretching of light caused by expansion, to calculate distances. And with thousands, then millions of distance measurements, they could plot galaxies in 3 dimensions. A pattern emerged. And it was nothing anyone expected. Galaxies are not scattered randomly. They are arranged in an enormous web-like structure stretching across the entire observable universe. Long filaments of galaxies, like threads of light, connect massive clusters at their intersections. Thin sheets and walls of galaxies separate vast regions. And between these filaments, sheets, and clusters, there are voids, not small gaps, not modest empty patches. Voids hundreds of millions of light years across containing almost nothing. The first major void was discovered in 1981 by Robert Kirshner and his colleagues. They were surveying galaxy positions in the constellation Boats, expecting a fairly even distribution. Instead, they found a sphere roughly 330 million light-years in diameter, containing only about 60 galaxies. A typical region that size should contain around 10,000. The Boats void has 60. That is 99.4% fewer galaxies than expected. Imagine a city the size of London, with all its millions of buildings, and then replace it with a flat, empty plain containing only 60 small sheds scattered across the entire area. That is the Boats void. And it is not unique. After Boats, astronomers found voids everywhere they looked. The giant void in the constellation Capricornus stretches roughly 1 billion light-years across. The Eridanus supervoid is similarly massive, about 1 billion light-years in diameter. There are dozens of known large voids and countless smaller ones. When you map the universe on its largest scales, voids are not the exception. They are the dominant feature. Most of the universe's volume is void. Picture a kitchen sponge. The solid part of the sponge, the material you can touch, forms a connected web of walls and threads. But most of the sponge's volume is the holes, the air pockets, the empty spaces surrounded by thin walls of material. The cosmic web looks like this. Galaxies and galaxy clusters form the thin walls and threads. Voids are the holes. And the holes are far larger than the walls. What would it be like inside one of these voids? Consider an observer on a planet orbiting a star in a galaxy near the center of the Boats void. They look up at their night sky. What do they see? Almost nothing. the nearest significant concentration of galaxies would be more than 165 million light-years away in every direction. For comparison, our nearest large galaxy neighbor, Andromeda, is only 2.5 million light-years away. The Void observer would need a telescope far more powerful than anything we have built just to see that other galaxies exist. Without one, their sky would be profoundly dark, no Milky Way band stretching overhead, because their own galaxy would likely be a small, faint dwarf without a prominent disk. No neighboring galaxies visible to the naked eye, just stars in their own small galaxy and, beyond them, absolute blackness. Their entire understanding of the universe would be shaped by that emptiness. They might develop physics, chemistry, an understanding of stars and planets. But cosmology as we know it would be nearly impossible. They would see so few distant galaxies that they might conclude the universe is almost entirely empty. They might never discover the cosmic web of filaments and clusters that we can see from our relatively crowded vantage point. This is a sobering realization. Our understanding of the universe depends on where we happen to be located. We are lucky to sit in the local sheet, a relatively dense structure on the edge of a void, but near enough to filaments and clusters that our telescopes can map the cosmic web. If we were deep inside a void, our picture of reality would be fundamentally poorer. And the voids are not standing still, they are growing. This is where the story connects back to dark energy. In regions with less matter, gravity is weaker. Expansion faces less resistance, so voids expand faster than the average rate. Meanwhile, matter in overdense regions, the filaments and clusters, is held together by stronger gravity and expands more slowly or not at all. The result is a universe that becomes more extreme over time. Dense regions get denser. Empty regions get emptier. The rich get richer. The poor get poorer. Dark energy accelerates this process. As expansion speeds up, matter in voids has less time to migrate toward filaments before expansion carries it beyond reach. The voids stretch wider, the filaments thin out. The cosmic web, this beautiful architecture of light and shadow, is slowly being pulled apart. The few galaxies that do live inside voids tell their own quiet story. They are called void galaxies, and they tend to be small, dim, and lonely, mostly dwarf galaxies with limited gas and low rates of star formation. They rarely interact with neighbors because there are so few neighbors to interact with. Galaxy collisions and mergers, which trigger bursts of new star formation in denser environments, almost never happen in voids. So void galaxies evolve slowly, forming stars at a trickle, aging gradually, drifting in isolation. Some of these void galaxies are among the most pristine objects in the universe. They have been alone for billions of years, untouched by mergers or interactions. They still resemble what galaxies looked like in the early universe, making them valuable fossils for studying galaxy evolution. But they are also profoundly isolated. Quiet worlds in quiet galaxies in the quietest places the universe has to offer. And the origin of all this structure, the filaments, the clusters, the voids, traces back to the beginning of time. The pattern we see today is the amplified echo of tiny density fluctuations that existed shortly after the Big Bang. Regions that were 1 part in 100,000 denser than average eventually became the filaments and clusters where galaxies congregate. Regions that were 1 part in 100,000 less dense became the voids. So the cosmic web is not random. It is a fossil record of the infant universe, stretched and amplified by billions of years of gravity and expansion. Every void, every filament, every cluster of galaxies carries information about conditions that existed when the universe was less than a second old. But there is something more troubling about this architecture than its origin. The cosmic web is temporary. Dark energy is dismantling it. Voids are widening, filaments are stretching thin, and the horizon beyond which light can never reach us is creeping closer every day. The observable universe is not just empty and getting emptier. It is shrinking, and what it is shrinking toward is a loneliness so complete that future civilizations may never know the rest of the cosmos existed at all. Space is expanding. You have heard that before. But most people picture it wrong. They imagine galaxies flying apart through space like shrapnel from an explosion, objects moving away from each other across a fixed background. That is not what is happening. Space itself is stretching. The background is growing. Galaxies are not flying through space. They are sitting still while the space between them inflates. Every point in the universe is moving away from every other point, not because anything is pushing the galaxies, but because the fabric they are embedded in is getting larger. Imagine dots drawn on the surface of a balloon. As you inflate the balloon, every dot moves away from every other dot. No dot is at the center. No dot is moving across the surface. The surface itself is stretching, carrying the dots apart. The universe works the same way, but in 3 dimensions instead of 2. And here is the critical detail. The farther apart 2 objects are, the faster they appear to recede from each other. This is because there is more space between them to stretch. If every meter of space grows by a tiny fraction each second, then 1,000,000 meters of space grows by 1,000,000 times that fraction. 2 objects separated by twice the distance recede at twice the speed. 3 times the distance, 3 times the speed. This relationship is described by the Hubble constant. Current measurements put it at roughly 67 kilometers per second per megaparsec. A megaparsec is about 3.26 million light years. So for every 3.26 million light years of distance between us and a galaxy, that galaxy recedes at an additional 67 kilometers per second. At modest distances, this recession is slow. Andromeda, only 2.5 million light years away, is actually falling toward us because gravity between our galaxies overpowers the local expansion. But at greater distances, expansion dominates. A galaxy 1 billion light years away recedes at roughly 20,000 kilometers per second. A galaxy 5 billion light years away recedes at roughly 100,000 kilometers per second. And at some distance, the recession velocity reaches the speed of light. This happens at approximately 14 billion light years in the current universe. Beyond that distance, galaxies are receding faster than light. And before you object that nothing can travel faster than light, remember these galaxies are not traveling through space faster than light. Space itself is expanding faster than light can cross it. Relativity forbids objects from moving through space faster than light. It says nothing about space itself stretching at any rate it pleases. Light emitted by a galaxy receding faster than light will never reach us. The photons leave the galaxy aimed in our direction, traveling at the speed of light through local space. But the space between us and that galaxy is stretching faster than the light can cross it. The photons make progress, but the distance they need to cover grows faster than they can close it. Imagine swimming upstream in a river. You are swimming at full speed, making progress through the water, but the current is faster than you can swim. You move forward through the water, but the water carries you backward faster. You lose ground despite your best effort. Light from these distant galaxies is in the same situation, swimming forward through expanding space, but losing the race. This defines a boundary called the cosmological horizon. Beyond this horizon, objects are causally disconnected from us. We can never observe them, never receive their light, never interact with them in any way. They exist, presumably, but they are forever beyond our reach. And here is the part that changes everything. This horizon is not fixed. It is moving inward. Because the expansion of space is accelerating, driven by dark energy, more and more galaxies are crossing the horizon every day. Galaxies that are currently within our observable universe but near the edge will eventually be carried beyond it. Their light will stretch to longer and longer wavelengths as they recede faster and faster. The photons will lose energy, shifting from visible light to infrared, from infrared to microwave, from microwave to radio waves, until they carry so little energy they become undetectable by any conceivable instrument. From our perspective, that galaxy does not explode or vanish in a flash. It fades. Slowly, imperceptibly, its light redshifts into nothingness, like a ship sailing away from shore, growing smaller, dimmer, until it drops below the horizon and is gone. The most distant galaxies disappear first, then slightly closer ones, then closer still. The observable universe is shrinking from the outside in, like a circle of firelight contracting as the flame dies down. But there is a flaw to this shrinkage. Objects that are gravitationally bound to each other do not participate in cosmic expansion. The Milky Way and Andromeda are falling toward each other. Our local group of about 80 galaxies is held together by mutual gravity. Expansion cannot pull apart what gravity has already claimed. So our local neighborhood will survive, at least for a while. Over the next several billion years, the Milky Way and Andromeda will collide and merge into a single large elliptical galaxy. The other galaxies in our local group will eventually be absorbed as well. This merged supergalaxy will remain intact, held together by its own gravity, even as everything beyond it recedes past the horizon. And then comes the loneliness. Observers in that future merged galaxy will look outward and see nothing. No other galaxies, no cosmic web, no clusters or filaments, just their own galaxy. A single island of stars in an ocean of darkness, stretching in every direction to infinity. The rest of the universe will still exist, but it will be permanently inaccessible. No signal, no light, no gravitational wave from those distant galaxies will ever arrive. And it gets worse. The cosmic microwave background, the faint afterglow of the Big Bang that fills the sky today at a temperature of 2.7 Kelvin, will also fade. As space expands, this radiation stretches to longer wavelengths and lower energies. Over trillions of years, it will redshift from microwaves to radio waves, to wavelengths longer than planets, longer than solar systems. Its temperature will drop below 1 Kelvin, below 1/10 of a Kelvin, approaching absolute zero so closely that no instrument could ever distinguish it from perfect silence. The most direct evidence of the Big Bang will be erased. Future civilizations in that lonely galaxy will have no way to discover that the universe had a hot, dense beginning, no way to measure cosmic expansion, because there will be nothing visible to measure it against, no way to infer the existence of dark energy, because every galaxy they could have compared to will be gone. They will develop physics. They will understand atoms and stars and gravity, but cosmology, the study of the universe's origin and fate, will be impossible. Every clue will have been carried beyond the horizon, by the very expansion those clues would have revealed. We live in a privileged window, a brief era when the universe is still observable, when distant galaxies still shine in our telescopes, when the CMB still whispers the story of creation, when we can still piece together where everything came from. And where everything is going. That window is closing, and it will never open again. But how did the universe end up with precisely the right conditions to create this window in the first place? The answer is hiding in the first fraction of a second after the Big Bang, in an event so violent and so brief that it makes everything that followed look like slow motion. The universe is uniform. Remarkably, almost suspiciously uniform. Look in one direction and measure the temperature of the cosmic microwave background. Then look in the exact opposite direction, billions of light years away. The temperature in both directions is 2.7 Kelvin. They agree to within 1 part in 100,000. This should not be possible. For two regions of space to have the same temperature, they need to have been in contact at some point. Heat flows from hot to cold. Given enough time, any two regions that can exchange heat will reach the same temperature. But to exchange heat, they need to be able to communicate. Light, the fastest possible messenger, needs time to travel between them. The two patches of sky on opposite sides of the observable universe are separated by roughly 93 billion light years. The universe is only 13.8 billion years old. Light has had 13.8 billion years to travel. These two regions could never have been in contact. Light from one could never have reached the other. They should have no idea what temperature the other is, and yet they match perfectly. This is called the horizon problem, and for decades it sat at the center of cosmology like an open wound. An uncomfortable fact that the standard Big Bang theory could not explain. The solution came in 1980 when physicist Alan Guth proposed something extraordinary. He called it cosmic inflation. The idea was breathtaking in its audacity and elegant in its consequences. Guth proposed that in the first unimaginably tiny sliver of time after the Big Bang, before a single proton had formed, the universe underwent a period of exponential expansion. Not the slow, steady expansion we see today, something vastly faster. Space doubling in size, then doubling again, then again, over and over. In a time so short, it has no meaningful human equivalent. The numbers are almost impossible to state clearly. In roughly 10 to the negative 32nd power seconds, a span of time about 1,000,000 trillion times shorter than the time it takes light to cross a single proton. The universe expanded by a factor of at least 10 to the 26th power. That is 100 million trillion times larger. Some models suggest the expansion factor was far greater still. Before inflation, the entire region that would become our observable universe today was smaller than a proton. A single tiny patch, small enough to have been in perfect thermal contact, to have reached a uniform temperature throughout. Then, inflation stretched that patch to cosmic scales in an instant, preserving the uniformity that had been established when everything was in contact. After inflation ended, normal expansion took over, slow, gradual, the kind Hubble measured. But the uniformity was already baked in. The CMB we see today, that remarkably flat temperature map across the entire sky, is a photograph of that tiny uniform patch stretched across 93 billion light years. Inflation solves another puzzle too. The universe is geometrically flat. In general relativity, the universe can have three possible shapes. Positive curvature, like the surface of a sphere where parallel lines eventually converge. Negative curvature, like a saddle where parallel lines diverge. Or flat, like a plane where parallel lines stay parallel forever. Observations show the universe is flat to extraordinary precision. But flatness is unstable. A universe with any initial curvature will see that curvature amplify over time as it expands. For the universe to be flat today, it would need to have been tuned to flatness at the Big Bang with absurd precision, like balancing a pencil perfectly on its tip and having it stay there for 14 billion years. Inflation explains this effortlessly. When something expands by a factor of 10 to the 26th power, any initial curvature gets stretched away. The observable universe becomes such a tiny patch of whatever the total universe looks like. That curvature within it becomes completely undetectable, like zooming in on a sphere so closely that the surface looks perfectly flat. Inflation zoomed in on the universe and flattened it. But inflation's most important contribution for our story is what it did with quantum mechanics. During inflation, the universe was subject to quantum fluctuations. This is unavoidable. Quantum mechanics says that fields cannot be perfectly smooth. They fluctuate randomly at the smallest scales, uncertain and restless, governed by the Heisenberg uncertainty principle. Normally, these fluctuations are microscopic. They happen at scales far smaller than atoms and have no large-scale consequences. But during inflation, space was stretching at an extraordinary rate. Quantum fluctuations that existed at subatomic scales were suddenly being stretched to enormous sizes. A fluctuation smaller than a proton got inflated to the size of a galaxy cluster. The randomness of quantum mechanics got written across cosmic scales. These stretched fluctuations became density variations in the early universe. Where the quantum field had slightly more energy, matter was slightly denser after inflation ended. Where it had slightly less energy, matter was slightly thinner. These differences were tiny, about 1 part in 100,000. But they were there, imprinted on the gas and radiation that filled the universe when inflation ended. You can see them today. The cosmic microwave background is not perfectly smooth. It has faint temperature variations, tiny hot and cold patches scattered across the sky. Those patches are the direct image of quantum fluctuations that existed before any star, any galaxy, any atom. They are the fingerprints of quantum mechanics stretched to the size of the observable universe. And they are the seeds of everything. Those 1 part in 100,000 density differences were enough for gravity to work with. Denser regions pulled surrounding matter inward. Over hundreds of millions of years, they grew. Gravity amplified the tiny initial differences into the first clouds of gas, the first stars, the first galaxies. The cosmic web of filaments and voids that astronomers mapped in 3 dimensions traces directly back to the specific pattern of quantum fluctuations that inflation stretched to cosmic scales. The voids we explored earlier are not random. They mark the regions where the quantum field happened to have slightly less energy during those first moments of inflation. The filaments and clusters of galaxies sit where the field had slightly more. The entire architecture of the observable universe is a map of quantum randomness, frozen in place by inflation and then amplified by gravity over 13 billion years. This makes inflation one of the most profound ideas in all of science. It connects the largest structures in the universe to the smallest possible scales of quantum physics. It explains why the universe is uniform, why it is flat, and why it has the particular pattern of structure that allows galaxies and stars and life to exist. But it also raises a question that inflation does not fully answer. Why did those quantum fluctuations have exactly the amplitude they did? 1 part in 100,000 turned out to be almost precisely the right value for structure to form. Too large, and the fluctuations would have collapsed directly into black holes before stars could form. Too small, and gravity would never have been strong enough to build galaxies at all. The universe's emptiness, the vast voids, the thin filaments, the enormous distances between galaxies, flows directly from that one number. Change it, and you change everything. And yet, we have no deep explanation for why it took that particular value. It is one of the most fundamental facts about the universe we live in, and it points towards something even more unsettling. The conditions that allowed us to exist may be far more fragile and far more precisely balanced than anyone would like to believe. There is a number at the heart of everything we have discussed tonight. 1 part in 100,000. That is how different the densest regions of the early universe were from the least dense. That tiny difference, smaller than the width of a human hair compared to the distance across a city, determined the entire large-scale structure of the cosmos. Every galaxy, every void, every filament, every cluster. All of it traces back to that single ratio, and that ratio had to be almost exactly what it was. Not approximately, not within an order of magnitude. It had to land inside a window so narrow that calling it a coincidence feels deeply unsatisfying. Too large, and the early universe collapses into black holes before a single star ignites. Too small, and gravity never wins, never pulls matter together, and the universe remains a thin, featureless gas spreading forever into silence. Let us walk through both failure modes carefully, because they reveal something important about why emptiness is a condition of our existence, rather than a flaw in the universe's design. Imagine the fluctuations had been 10 times larger, 1 part in 10,000 instead of 1 part in 100,000. Gravity would have been 10 times more effective at pulling dense regions together. The collapse would have been faster and more violent. Gas clouds would have compressed so rapidly that they reached enormous densities, before any stable structure could form. Instead of igniting as stars, these clouds would have collapsed directly into black holes. The early universe would have been full of black holes, separated by thinning gas that had no time to form galaxies or stellar systems. No stars would shine. No planets would orbit. No chemistry beyond the simplest hydrogen reactions would ever occur. Life, which depends on the heavy elements forged inside stars and scattered by supernovae, would have been permanently impossible. Now imagine the fluctuations had been 10 times smaller, 1 part in a million instead of 1 part in 100,000. Gravity would have been 10 times weaker relative to the smoothness of the early universe. Dense regions would have pulled on surrounding gas, but the pull would have been too gentle. The universe was also expanding during this time, carrying matter apart. With weaker initial density contrasts, expansion would have won the race against gravity in almost every region. Gas clouds would have dispersed before they could concentrate enough to ignite fusion. Galaxies would never have formed. The universe would have expanded forever as a thin, cooling mist of hydrogen and helium, growing emptier and darker with every passing billion years, never producing a single star. The observed value of 1 part in 100,000 sits in a narrow corridor between these two catastrophic outcomes, and we do not have a deep physical explanation for why it landed there. This is part of a broader pattern that physicists call fine-tuning. The universe appears to have been set up with many of its fundamental parameters, adjusted to values that permit complex structures and life. Change any one of them significantly, and the universe becomes sterile, and the density fluctuation amplitude is one of the most striking examples. The strength of gravity itself is another. If gravity were significantly stronger, stars would burn through their fuel in thousands of years instead of billions, leaving no time for planets to form or life to evolve. If gravity were much weaker, gas clouds might never collapse into stars at all. The expansion of the universe would overpower gravity at smaller scales, and structure formation would halt long before galaxies appeared. The ratio of matter to antimatter in the early universe is another example. When particles formed after the Big Bang, they came in matter-antimatter pairs. For every billion antiparticles, there were 1 billion and 1 particles. That tiny excess of 1 part in a billion is what produced all the matter in the universe today. Everything you see, every star, every galaxy, every atom in your body, comes from that tiny leftover after matter and antimatter annihilated each other. If the ratio had been perfectly equal, everything would have annihilated, and the universe would contain nothing but light. The strength of dark energy provides perhaps the most extreme example. As we explored earlier, quantum field theory predicts a vacuum energy, 120 orders of magnitude larger than what we observe. Whatever mechanism reduces the theoretical value to the observed value must be extraordinarily precise. If it was slightly less precise, dark energy would be strong enough to have prevented any structure from forming. Immediately after the Big Bang, galaxies would never have had the chance to appear. These are not independent puzzles. They point toward a single uncomfortable reality. The universe we inhabit is one where a remarkable number of parameters take values that allow complex structure to exist, and we have no agreed upon explanation for why those values are what they are. Physicists have proposed several responses to this situation. One is that there is a deeper theory we have not yet discovered. Perhaps some future unified framework will show that all these values are not free parameters at all. Perhaps they are the only values logically consistent with a coherent universe, and we have simply not understood the logic yet. This is the most scientifically optimistic position. It says the fine-tuning is an illusion created by our incomplete knowledge. Another response is the multiverse. If there are vast numbers of universes, each with different values of the fundamental parameters, then the observation that we live in a life-permitting universe requires no special explanation. We could only arise in a universe where the parameters allow us to exist. So naturally, that is the kind of universe we find ourselves in. This is not a coincidence. It is a selection effect. We are here because here is the only kind of place that could produce us. This argument is called the anthropic principle, and it makes many physicists deeply uncomfortable because it feels less like an explanation and more like an acknowledgement that no explanation is possible. It shifts the question from why the parameters are what they are to why our universe is among the lucky ones, and it requires accepting the existence of countless other universes we can never observe or test. But there is a quieter implication hiding inside the anthropic principle that connects directly to the emptiness we have been exploring all night. We observe the universe to be mostly empty, because a mostly empty universe is one of the conditions required for life to exist. Too dense and black holes dominate. Too smooth and no structure forms. The specific level of emptiness we observe, the vast voids, the thin filaments, the enormous distances between galaxies, is not arbitrary. It is the level compatible with the existence of observers. The universe is empty for a reason, and that reason is us. Not that we caused the emptiness, not that the universe was designed around our needs, but that the emptiness and our existence are both consequences of the same initial conditions, and you cannot have one without the other. The cosmos could not have produced conscious matter in a universe significantly denser or significantly emptier than this one. And yet, even within these finely balanced conditions, emptiness wins in the long run. The structures that exist now are temporary. The galaxies shining tonight will eventually go dark, the stars will burn out, the voids will widen, and the universe will move, slowly and irreversibly, toward its final state. A state we have been circling all night without naming directly. The state that the second law of thermodynamics has been pointing toward. Since the beginning of time, everything ends, not dramatically, not in fire or flood or some cosmic catastrophe arriving without warning. The universe ends the way a fire dies when the last piece of wood finally turns to ash. Slowly, quietly, without announcement. The light goes out, and what replaces it is not darkness so much as stillness. A cold, perfect, permanent stillness that will last longer than any number we have names for. This is the fate that physics points toward. And to understand it, you need to follow time forward into scales that make the current age of the universe look like the opening frame of a film that runs for billions of years. We are currently about 13.8 billion years into the universe's existence. By cosmic standards, it is early. Stars are still forming. Galaxies are still colliding and merging. The universe is in the middle of what astronomers call the stelliferous era, which simply means the age of stars. This era began a few 100 million years after the Big Bang, when the first stars ignited. It will continue for a very long time yet. Red dwarf stars, the smallest and most common type, burn so slowly and so efficiently that some alive today will still be shining 100 trillion years from now. 100 trillion years. The entire current age of the universe, every billion years of cosmic history from the Big Bang to this moment, would need to repeat itself 10,000 times to reach that point. And even then, the story would barely be starting. But eventually the gas runs out. Star formation requires cold gas clouds dense enough for gravity to ignite fusion. Galaxies have a finite supply. Over billions of years, that supply gets used up, expelled into intergalactic space by supernova explosions, or stretched beyond reach by expansion. The rate of star formation has already been declining for several billion years. It will continue to slow until, around 100 trillion years from now, it stops almost entirely. The last stars will form from the last available gas. After that, only existing stars remain, burning down like candles with no way to relight. One by one, over trillions of years, the stars exhaust their hydrogen fuel and die. Massive stars go first, exploding as supernovae, leaving behind neutron stars or black holes. Medium stars like our Sun shed their outer layers as planetary nebulae and collapse into white dwarfs, dense hot remnants about the size of Earth. Small red dwarf stars simply cool and dim until they fade below detection. By about 10 to the 15th power years from now, 10 quadrillion years, essentially all stars will have burned out. No more fusion. No more starlight. The universe enters what physicists call the degenerate era. The sky, from any vantage point, would be perfectly dark. The only objects remaining would be white dwarfs slowly cooling, neutron stars, black holes, brown dwarfs that never ignited, and cold planets drifting untethered through empty space. These remnants do not disappear quickly. White dwarfs cool over trillions of years, radiating their stored heat into the surrounding darkness, dropping degree by degree toward absolute zero. Eventually they become black dwarfs, cold dark objects with no internal heat and no light of any kind. They are essentially dead stars made of crystallized carbon and oxygen, drifting silently through expanding space. Inert. Permanent. Cold. During this same period, something else is happening inside galaxies and galaxy remnants. Stars and stellar remnants interact gravitationally as they pass near each other. When two objects fly close together, they exchange momentum, One speeds up, gaining energy and eventually reaching escape velocity, flying out of the galaxy entirely. The other slows down, losing energy, falling deeper into the galactic center. Over time scales of about 10 to the 20th power years, this process, called gravitational evaporation, ejects the vast majority of objects from galaxies. Roughly 90% of stellar remnants gradually gain enough energy from close encounters to escape. They drift off into intergalactic space, isolated and cooling, never to interact with anything again. The remaining 10% fall inward toward the central supermassive black hole, eventually being absorbed. By this point, what we called a galaxy has ceased to exist as any recognizable structure. The central black hole sits alone, perhaps surrounded by a handful of slowly spiraling remnants, while the vast majority of the galaxy's former contents drift as isolated objects through space that is now almost inconceivably empty. But black holes themselves are not permanent. In 1974, Stephen Hawking showed that quantum effects cause black holes to slowly radiate energy. Near a black hole's event horizon, quantum fluctuations produce pairs of particles. One falls into the black hole, the other escapes. The escaping particle carries energy away, and that energy must come from somewhere. It comes from the black hole's mass. Over time, the black hole loses mass, shrinks, and eventually evaporates completely. The rate of evaporation depends on mass. Larger black holes evaporate more slowly. A black hole with the mass of our Sun would take roughly 10 to the 67th power years to evaporate completely. The supermassive black holes at the centers of galaxies, with masses of billions of suns, take far longer. A billion solar mass black hole requires about 10 to the 100th power years to disappear. 10 to the 100th power. That number is called a googol. There is no physical intuition for it. The current age of the universe, 13.8 billion years, is roughly 10 to the 10th power years. A googol is 10 to the 90th power times longer than that. Every second that has passed since the Big Bang would need to be multiplied by 10 to the 90th power to reach a googol years. And yet, eventually, even the most massive black holes evaporate. Their final moments are dramatic. As a black hole loses mass, it radiates faster. Evaporation accelerates. In its last fraction of a second, the remaining mass converts entirely to radiation in a brief, brilliant flash of gamma rays. Then nothing. The black hole is gone. After all black holes have evaporated, what remains? Cold black dwarfs drifting through expanding space. Isolated neutron stars, photons from every explosion and every flash of light that ever occurred, now stretched to wavelengths longer than galaxies, carrying almost no energy. Neutrinos from ancient supernovae. And dark matter, whatever it is, still present but spread across distances so vast that the average density of the universe approaches zero. But even the black dwarfs may not be permanent. Some theories predict that protons, the particles at the core of every atom, eventually decay. If protons have a lifetime of around 10 to the 40th power years, then over that timescale every black dwarf slowly dissolves. Its protons convert into lighter particles, positrons and neutrinos and photons, which drift away into space. The black dwarf quietly disappears, converted entirely into radiation that spreads through an expanding void. If this happens, then by about 10 to the 40th power years, matter in any conventional sense no longer exists. No atoms, no nuclei, no solid objects of any kind. Just a thin mist of particles and radiation at a temperature so close to absolute zero that the difference is unmeasurable. The universe has reached heat death. maximum entropy. Complete equilibrium, no differences in temperature anywhere, no gradients to drive any process, no way to extract energy and do work. Nothing happens. Nothing can happen. The universe does not end in this state, it simply stops changing. And that stillness persists not for billions of years, not for trillions of years, but for what is effectively forever. In that final accounting, the entire era of structure and complexity, stars and galaxies and life, and everything that has ever happened that we would recognize as significant, occupies the first vanishingly small fraction of the universe's total history. Everything that has ever mattered, every civilization that has ever risen, every thought that has ever been thought, occurs in what is, from the universe's perspective, a single opening moment before the long silence begins. And so we arrive here, at the end of the journey, not at the heat death, not at the final silence, but at this moment, the one you are living right now. A body at rest, a mind growing quiet, a consciousness that somehow, against all odds, finds itself awake inside the most improbable arrangement of matter the universe has yet produced. We started tonight with a lie the night sky tells, all that light, all that apparent abundance, concealing a darkness so total and so permanent. That emptiness is not just the condition of most of space, but the final destination of all of it. We walked through the numbers. We felt the vertigo of a cosmos where stars occupy less of reality than a proton occupies the Earth. We discovered that even the matter we can see and touch is only 5% of everything, with the rest divided between invisible dark matter we cannot identify, and dark energy we cannot explain. And we found that the emptiness has architecture. The cosmic web of filaments and voids, the largest pattern ever mapped, is itself a fossil record of quantum fluctuations that existed before a single particle had formed. The voids are not failures of structure. They are the necessary counterpart to everything that has density. You cannot have galaxies without voids. You cannot have filaments without the emptiness surrounding them. The universe's emptiness and its structure are two sides of the same coin, minted in the first fraction of a second, and spent over 14 billion years of cosmic history. But here is what we have been circling without saying plainly. You exist in the single most extraordinary moment in all of this. Not the most dramatic, not the most energetic, the most extraordinary. The universe is 13.8 billion years old. Stars will continue forming for at least another 100 trillion years. Beyond that lies the slow cooling of the degenerate era, the evaporation of black holes over timescales measured in googles, and then the final stillness of heat death stretching effectively forever. If you placed the entire history of the universe, from the Big Bang to heat death, on a single timeline, the era in which conscious observers can exist would occupy a thin line near the very beginning, a line so thin it would be invisible to any eye examining the full timeline. We are in that line, right now, tonight, and within that already impossibly narrow window, there is a smaller window still, the window during which the universe is observable, when distant galaxies still shine, when the cosmic microwave background still whispers the story of the Big Bang, when the full cosmic web is still visible to telescopes pointed at the sky. That window is already narrowing. In a few trillion years, it will be closed permanently. Future observers will inherit a universe so stripped of evidence that the Big Bang, dark matter, dark energy, the cosmic web, everything we have spent tonight exploring, will be completely beyond their ability to discover. They will have stars. They will have physics. But cosmology as a science will be impossible. the universe will have erased the clues before they arrived to look for them. We have not arrived too late. We are living in the last era when the universe can be fully read. This should change how you feel about what you know. Every measurement ever made of a distant galaxy, every photograph from the Hubble Space Telescope or the James Webb Space Telescope, every calculation of the universe's expansion rate, every detection of the cosmic microwave background. These are not just scientific achievements, they are acts of preservation. We are reading a document that is slowly burning, and we are the only readers who will ever have access to the full text. Now, bring it closer. Bring it all the way down from the scale of the observable universe to the scale of a single body lying still in a quiet room. You are made of atoms. Those atoms were forged inside stars that lived and died before our sun was born. The carbon in your cells was assembled in the core of a red giant that exploded billions of years ago. The oxygen you breathe was scattered into space by supernovae and gathered again by the gravity of a forming solar system. The iron in your blood was produced in the final moments of a massive star's death, released in a flash of energy billions of times brighter than the sun. You are not separate from the universe's story. You are a chapter of it, a chapter that could only have been written at this particular point in time, in this particular corner of a galaxy that sits in this particular filament of the cosmic web, because the density fluctuations from inflation produced these conditions and no others. The emptiness surrounding you is not a backdrop. It is the context that makes you possible. In a universe packed with matter, everything would have collapsed into black holes before the first star ever shone. In a universe too smooth, no star would have ever formed at all. The vast gulfs between galaxies, the voids hundreds of millions of light years across, the almost incomprehensible thinness of matter across cosmic scales, all of that emptiness is the price the universe paid. To produce the narrow, dense, star-forming filaments where solar systems like ours could exist, you are possible because the universe is mostly empty. And you are aware of it. This is perhaps the strangest fact of all. Matter has arranged itself in at least one tiny corner of this vast emptiness into a configuration that can look back at the whole and understand it, that can trace the journey from quantum fluctuations during inflation, to the cosmic web, to the formation of galaxies, to the death of stars, to the assembly of planets, to the emergence of life. To this moment, a mind resting quietly, following the thread of the longest story ever told. The universe does not know it is empty. It does not mourn the voids. It does not feel the loneliness of galaxies separated by millions of light years of nothing. It does not experience the slow cooling of the degenerate era, or the long silence of heat death. It just is. Expanding. Cooling. Thinning. Moving toward equilibrium with the patient indifference of physics. But you know. And that knowing, that capacity to hold the entire arc of cosmic history in a mind no larger than a small melon, sitting in a room on a small planet orbiting an ordinary star, in the outer arm of an unremarkable galaxy, that is the most improbable and the most significant thing the universe has done. The lights are going out, slowly over timescales beyond any number we can feel. Galaxies will fade beyond the horizon, stars will exhaust their fuel, the cosmic web will dissolve, the last black holes will flash briefly and disappear, and then the long stillness will begin, cold and dark and perfect and utterly without witness. But not yet. Right now, the stars are still burning, the galaxies are still turning, the cosmic microwave background still carries its ancient warmth across the sky. The universe is still telling its story, and you are still here to hear it. Let that settle over you now like the dark outside your window. Let the scale of it press gently down. The emptiness is real, the distances are real, the fate is real, and so are you, briefly and completely and remarkably. Your breath is slowing, your thoughts are loosening their grip on the details, the numbers, the scales, the time scales. Let them go. They will be there in the morning. The universe will still be expanding when you wake. The voids will still be growing. The stars will still be burning through their fuel. A little closer to the end, but still burning. And somewhere in the vast, quiet dark between galaxies, light is still traveling. Ancient light from stars that no longer exist, crossing distances that have no human equivalent, carrying no message, serving no purpose, witnessed by nothing. Except for one brief and extraordinary moment in the history of time by us. Close your eyes. You have earned the dark.